three presentations. Yeah, the first one is from Intel, from Mikhail, about temporal assertions. Yeah, maybe Mikhail, you can unmute and start. Okay.
Can you hear me?
Yeah, I can hear you. Yeah.
Okay, great. Thank you. So my name is Mikhail Moiseev, and together with Leonid Azarenkov and Ilya Klotchkov, we present temporal assertions in SystemC. So in current SystemC language, there are some assertions and error reporting based on SC report and SC report handler. There are also several convenient macros which can print message and stop SystemC simulation in case of a fatal error. We also can use C++ assertions and assertions from any C++ and SystemC libraries. In comparison with SystemC, in SystemVerilog there are much more features related to assertions. There are immediate assertions and concurrent assertions which can be placed in always blocks and in module scope as well. So in concurrent assertions, there are multiple forms of concurrent assertions. One of them is assert property. There is some precondition expression, temporal, time condition, and post condition. So there are also some features like combining assertion properties, some system functions, and so on. Inspired with SystemVerilog assertions, we propose to extend existing SystemC assertions with the temporal properties. So they will look similar to temporal SystemVerilog assertions and will be used in SystemC simulation and to generate equivalent SVA during high-level synthesis. We mostly thinking about hardware design, so we consider SystemC synthesizable subset here. In other words, these assertions are proposed for signal level or for cycle accurate SystemC. So temporal assertions, proposed temporal assertions can be placed in module scope and in thread process function scope. In module scope, there is a CT assert macro with 4 parameters. First one is precondition, time parameter, post condition, and activation event. Precondition and post condition are arithmetical or logical expressions which can be evaluated as Boolean. Temporal condition is just a specific number of cycles or time interval represented in cycles. And event is just some cycle event. Normally it's a clock, pos age, neck age, or both ages. There is also a shortened form of this CT assert macro just with 2 parameters, post condition and event. In this case, precondition is true and time is 0. It's really not temporal assertion, but convenient to use. In thread process function, there is the same CT assert macro, but with 3 parameters because event is not required as it's taken from a process function static sensitivity. And also there is a special CT assert loop macro, which intended to be used for accessing all or some elements of array or vector. Let's start with the temporal assertions in module scope. These assertions can access module fields like signals, ports, and so on. And they require an event. As I said, it's normally a clock, positive, negative, or both ages, but really can be any general event. So in first example, there is a CT assert A, time parameter 0, B, and event is clock negative age. So that means if A is true, that immediately at the same moment B must be true. So A and B is some general expressions. Here in first example, in first assertion, event is clock negative age. That means that A and B can be compared or can be evaluated only at this CLK negative age. The second assertion is almost the same, just time parameter is 1. That means if A is true at some clock negative age, at the next clock negative age, B must be true. We can use intervals with low minimal number of cycle and maximal number of cycle, and it's possible to omit this SC time parameter to have a shorter and more clear form. So there is more realistic example with several assertions. In this example, we have a SystemC module a.cpp with some constant clock input, input signal request, output signal response, some output port, response, some signal and vector of signals. And 4 assertions. So in first assertion, if request, next cycle response must be true. For these assertions, there is a automatically generated SystemVerilog assertion property, which is equivalent to SystemC1. It started with A10. A, it's a name of SystemC module, in our case is A, and 10 is a number of line. This SCT assert SystemC is in line number 10. So we have a tool called SystemC-to-Verilog Compiler, Intel SystemC-to-Verilog Compiler. So this tool was presented at the previous DVCon 2019, and currently it can generate SystemC-to-Verilog, and also can generate these temporal assertion, translate them into equivalent SystemVerilog assertions. So all the examples in these presentations, all the SystemVerilog is automatically generated by this tool. So temporal assertions in function scope can additionally access local variables of this function and member variables which modified in this function. Assertions in function can be placed in reset section before first wait, or just after reset section, but before main loop. There are 3 examples of SCT assert macro in function scope. They look similar to assertions in module scope, just we don't need event here. There is a special kind of assertions used inside of loops. It intended to access all or some elements of array, vector, of module, signal, port, and others. And here we have an example of a SCT assert loop inside of for loop with variable j. And it has normal parameters and additional 1 parameters, this variable j as the last parameter. It required to create assertions for each loop iteration. Normally, this expression A and B here depends on j, so it's j normally used as index, but can use in any other form. So let's go through several examples, temporal assertions in functions. So here in the left part, you can see a thread procs function, so SystemC function with a reset section. And there is 1 assertion in reset section and 1 assertion after reset section. The difference is that the first assertion executed during reset and after reset as well. And the second assertion executed only after reset. And there is in the right part, you can see automatically generated always FF block for this function. And there is a main if of reset with a reset section and main logic. And in main logic, you can see automatically generated second assertion. And the first assertion is inserted after this if, so it works during reset and after reset as well. So there is temporal assertions in loop. In our example here, we have one-dimensional vector E and two-dimensional vector A, and two assertions, one for E and one for A, and they are automatically translated into SystemVerilog assertions, which are placed in equivalent loops, in loops which are equivalent to SystemC loops. There is a piece of real code. It's an industrial module which implements a port of a standard protocol. And as it's a port, it has some ready, valid signals and some read, write burst, and these assertions check correctness of the protocol implementation. So I give you this example just to give some impression how it looks like in real code. So let me go through some implementation details. Implementation of a CT assert and a CT assert loop macros in SystemC simulation. These macros are replaced with several things. First of all, it's dynamic allocation of a CT property expression class instance, which captures precondition and postcondition expressions as lambdas to be able to evaluate these lambdas in future and store pre and post condition trace to check them in specified time or time interval. For each instance of a CT property expression class, there is a spawned method process created, which is sensitive to specified event or current thread static sensitivity event. In this spawned method process, this operator bracket of this class instance is executed. To ensure that there is exactly one instance of a CT property expression for each assertion, there is a static map which with some hash which check existing assertions and create a new one if required. All that is implemented in SystemC in C++11. That it's enough to support all the features. It's planned that these temporal assertions will be automatically translated to SystemVerilog assertions by any HLS tool. To simplify life of HLS tool designers, we provide a special mode. In this mode, a CT assert macro is replaced with a simple function, this CT assert and procs function, which is really empty, and just this function has an interface with all CT assert macro parameter. Using this function in some IST, which is abstract syntaxis tree, or another form of parsed code, is simple to extract all the function parameter and create the corresponding, the equivalent SystemVerilog assertion. The same thing is done for a CT assert macro in module scope, but as we cannot have here a function call, we create a variable with a unique name, variable of special type, which has a constructor with all the required parameters, including event finder. We have evaluated these assertions with a number of artificial designs and 5 industrial designs, A to E. Each of these designs has quite a big number of processes, and we inserted a number of assertions. To estimate performance of our assertions, we compared original design and design with assertions, and here you can see increasing of simulation time, SystemC simulation time. It's from 4 to 16%. To understand if these numbers are good or bad, we compared SystemC simulation with the Verilog simulation. We have translated each of these design to a SystemVerilog, and using one of commercial Verilog simulation tool, compared simulation time with and without assertions, and see almost the same number from 5 to 15% simulation time increase. And believing that this Verilog simulation tool is good, we can say that our implementation of SystemC assertions is also good enough. So, concluding the presentation, I would say that we demonstrated the possibility to implement subset of SystemVerilog assertions, some temporal assertions, using C++11. And we are planning to submit a proposal to SystemC language work group to include these kind of assertions into SystemC standard and in SystemC synthesizable standard. And these assertions are available in open source. You can find them at GitHub repository. And also you can find our tool officially called Intel Compiler for SystemC. It's also open sourced and available under Apache license. You can download, install, and try this tool together with these temporal assertions. So that's all from my side. Thank you for your attention.
Okay, thanks a lot. Are there any questions? I think you should be able to unmute your mic. Or not?
So I have a question. This is Daniel.
Yeah, then.
Okay, I just want to be sure you hear me. My question is, so did I got it right here? So the main focus of your current implementation is a synthesizable subset. Is this correct?
Yes, exactly.
Okay, is it straightforward, or what is your opinion if you would target also TLM stuff? Is there something planned, or what would be the effort here?
It's thank you. It's a really good question, and yeah, I think we need to consider how to extend these assertions to TLM, and what kind of TLM models can get benefit from these assertions. And I would be glad to get any feedbacks from you and from your colleagues, and maybe we can work on this topic together.
Mm-hmm. Okay, thanks.
Thank you, Daniel.
Okay, there are more questions. Okay, maybe one question from my side. Is it also possible to support sequences for the pre and conditions?
Generally, yes, it's possible, and when we plan this implementation, we try to cover a much bigger subset of SystemVerilog assertions, but finally decided to implement the most, from our opinion, the most important subset just as a first step. But of course, it's not a final solution. And yes, I think we can extend it for sequence.
Yeah, I think so. There's maybe another question inside the chat from Swaminathan. If there are multiple IPs running at different frequencies, how are the cycles computed for assertions?
Cycles are normally a clock period. So if there are different clocks, each assertion can operate on its own clock, so it's not a problem.
Okay. There are other questions. Okay.
So maybe can just jump in again and related. So of course, what is good that you now compared your stuff with SVA. Yeah, that's very good. In this context, have you made some, let's say, internal tables where you kind of compare with, of course, with respect now to this this RTL-like assertion style you currently have? How much support do you support from this SVA, let's say, language specification?
Do you mean how much features in percents or something like that?
Yeah, in some sense, if you look into the IEEE standard, right, then you have all these operators, and there is also a semantic even defined at the end. And of course, if you go in the full formal space, then you normally have this point that the tools then somewhere on page 850 say, okay, we are not supporting this and that for good reasons, because in the formal space you are at some point you die out with very complex assertions. So, but nevertheless, so of course I've seen here these examples which look good, no question. But have you started to make some comparison, or was it more what you have implemented was driven from what you needed, I assume, right?
So my feeling is that we implemented 10 to 20% of SVA features, but from my opinion, it's most usable 10 or 20%. And we have evaluated other features, and some of them can be implemented. Some of them can be implemented in very difficult or inconvenient way. So yeah, maybe I will share some additional information in this at this GitHub repository as additional presentation with more details, and we can discuss it. Yeah.
Okay, yeah, this would be great. Yeah.
Thank you.
Thanks.
Okay, is there another question? Okay, otherwise, thanks a lot, Mikhail.
Thank you.